In this video, I'd like to discuss parallel and perpendicular lines. We're going to start with parallel lines, and I'd like to start by, in this video, I'd like to talk about parallel and perpendicular lines. We're going to start with parallel lines, and to start this, I'd like to actually plot 2 points. So the first point will be 3, 6, and the second order pair will be -3 and 2. So let's plot these 2 points, and we're going to see that we go to the right 3 units on the x-axis and up 6 units. So the first order pair will be plotted here. This will be our first point. The second order pair will be to the left 3 units and up 2 units. Alright, so what I'd like to do now is find the slope of the line represented when I draw it through these 2 points. Okay, now you'll recall our slope formula is m is equal to the difference in y's, or the difference in dependent variables. So in this case it'd be 6 minus 2 over the difference in independent variables. So that would be, in this case, 3 minus -3. So this will produce 4 over 6, which will be reduced to 2/3. So our slope for this line is 2/3. And you'll see I then want to go ahead and plot another set of ordered pairs. All right, and the second set of ordered pairs I'd like to plot are 3, 3 and 6, 5. So 3, 3 will be to the right 3 up 3 units, so plotted right here by this point. And the second one is to the right 6 units up 5 units. So we're right here. All right, so I'd like to again find the slope of this line represented with these 2 ordered pairs. So I'm going to go ahead and, again, with my slope formula, I'm going to have 5 minus 3, difference in y's, over the difference in x's, so 6 minus 3. So in this case, I get 2/3. Now, these look parallel, especially if I could draw them straight. They certainly look parallel, and what we see here is that these 2 parallel, seemingly parallel lines have the same rate of change. So from every point that you pick on the line to get to another point on the line, you're going to continue to have the same rate of change, which means as long as they don't have the same starting point, they will continue to be parallel. Now, if they have the same starting point, then technically they would overlap, because if they both have the same starting point, let's say this y-intercept, and it's rise 2, run 3, then they will continue to overlap, and we do not consider that parallel. Okay, in that case they would be coinciding lines, but they would not be parallel lines. So again, these are parallel lines because they do not have the same y-intercept, but they do have the same slope. And this brings us to our first theorem. The theorem states that 2 non-vertical lines are parallel if and only if their slopes are equal and they have different y-intercepts. Now, we saw the last 2 parts of this. I want to highlight one part we didn't really talk about, and this idea that they have to be non-vertical. Okay, non-vertical lines. And again, because non-vertical vertical lines would have an undefined slope. So that's one of the reasons we say non-vertical. And another reason would be that non-vertical lines, unless it is on the y-axis, unless the vertical line is the y-axis, it would not have a y-intercept. For my first problem, I would like to find the equation of a line that is parallel to 2x plus y is equal to 6, so the line that is represented by this equation, but that also contains the point ordered pair 2, 3. All right, so again, we want it parallel to this equation, the line that represents this equation, but the line must also go through this ordered pair. Okay, so the first thing we need to do, because we know something about parallel lines, we know for a fact that they have the same slope, we need to find the slope of the equation that I've already given. To do that, I would like to go ahead and solve for y. So I'm going to subtract 2x to both sides. I have y is equal to -2x plus 6. This puts it into slope-intercept form, which is y equals mx plus b, where m represents your slope. It's the coefficient of your x variable, your input variable, and in this case is -2, so m is equal to -2. So we know our equation for the new line, for the parallel line, will have a slope of -2. However, we don't know what the y-intercept will be. We know for a fact that this b will not be 6. What we should then use is our point slope form. Point slope form, if you recall, is y minus y1 is equal to m, the slope, times x minus x1, where x comma x1 comma y1 is an ordered pair on the line. So we do have an ordered pair on the line. It's 2 comma 3. So the x1 value will be 2 and the y1 value will be 3. So let's substitute all the values we have. We want to keep the variable y because we need an output variable or a dependent variable. We do want to substitute a value for y1, and in this case will be 3. We do have a value for m, our slope, which is -2. And we do have a value for x1, which would be 2 from the ordered pair I gave you. From here, now this is technically an equation. So this, according to my directions, this is an acceptable response. I'd like to find an equivalent equation, though, in slope-intercept form. So in other words, I'd like to solve this for y. Distribute the -2 to the quantity x minus 2, so you'll have y minus 3 is equal to -2x plus 4. Add 3 to both sides to the constant. And so we have y is equal to -2x plus 1. So this is an equation that is parallel to 2x plus y is equal to 6, but contains the point 2 comma 3. Now I would like to discuss perpendicular lines. To do that, to visually see perpendicular lines, I'm going to start by graphing a set of ordered pairs. The first ordered pair would be 4 comma 5, and the second one will be -4 comma -1. So the first one, I'd like to go to the right 4 units and up 5 units, and the second ordered pair to the left 4 and down 1. I'm now going to graph the line containing these 2 points, drawing it as straight as I possibly can. And I'd like to find the slope of these two so that when I do the second line, I then can compare and contrast these similarities and differences. So m is equal to, we have 5 minus -1 over 4 minus -4, which produces 6 over 8, and reduced, this should be 3/4. So my slope of the first red line is 3/4. The second set of points I'd like to plot will be 3 comma -2 and 0 comma +2. So first one, I'm going to go to the right 3 units, down 2 units, plot this point, and then 0 comma 2 is just simply up 2. Okay, now I'd like to go ahead and write or draw the line containing these 2 points as straight as I possibly can. Now while I'm drawing this, remember the definition of perpendicular means that these meet at a 90-degree angle, and they certainly appear to meet at a 90-degree angle. So they appear to meet at a 90-degree angle. I'd like to then go ahead, given that these are perpendicular lines, I'd like to go ahead and find the slope of the second order pair, and like I said earlier, compare and contrast. So we have m is equal to, we have -2 minus 2, and we have 3 minus 0, so this would be -4/3. Okay, so let's now compare and contrast the slopes and also the y-intercepts. Okay, notice the slopes are not equal. So as parallel lines had equal slopes, these do not. But notice that there is certainly relationship. All right, they appear to be, they actually are, opposite and then also reciprocal. So notice that the fraction has been flipped, so 3/4 becomes 4/3, and then they are opposite. So whereas 3/4 was positive, 4/3 is negative. So they're opposite and reciprocal. okay? Looking at the graph, we can clearly see that the intercept, the y-intercept for both of these is positive 2. So these can actually have the same y-intercept. Now, do they always need to have the same y-intercept? No, that is not a pattern. They don't always have them, but it's possible to have the same y-intercept. This brings us to our second theorem, which states that two non-vertical lines are perpendicular if and only if the product of their slopes is -1. So using the previous example that we just saw, we had one slope equal to 3/4. We then had the perpendicular slope equal to, by the way, this upside down t represents perpendicular. We had that slope equal to -4/3. And if we multiply both of these slopes, so 3/4 times -4/3, we will get -12/12, which then reduces to be -1. So perpendicular slopes always have a product of -1. Our second equation is to find a line that is perpendicular to x plus 3y is equal to 6 and also containing the point 1, -2. So similarly to the parallel lines, what we have to do is first find the slope of the equation that we're given. So we are given x plus 3y is equal to 6. We must solve this for y, so we subtract x to both sides. We then have 3y is equal to -x plus 6. I'm putting this into slope-intercept form. I then divide by 3 to all terms, and so I have y is equal to -1/3 x plus 2. All right, so this is slope-intercept form of the equation that we are given. So what we want to do now is find a line that is perpendicular to this but also contains the point 1, -2. To do that, I must first find the perpendicular slope. So we know the slope over here for this original equation, m is equal to -1/3. The perpendicular slope, remember upside down t represents perpendicular, is actually equal to +3/1, which is really just 3. So with that, again, just like we did with parallel lines, we're going to use point slope form. So y minus y1 is equal to m times x minus x1, where x1 and y1 are an ordered pair, which we are given. So we have y minus -2 is equal to the slope, which is 3, times x minus 1. Again, if it just says find an equation, well, technically this is an equation that represents the line that would be perpendicular to the equation given and also contains the point 1, -2. However, typically we prefer to write this in slope-intercept form. Slope-intercept form is also more familiar with people and it's easier for most people to graph. So I'm going to simplify this into y plus 2 is equal to 3 times x minus 1. This would be your answer if keeping it in the point slope form. And I'm going to go ahead and solve this for y. So distribute the 3. Y plus 2 is equal to 3x minus 3. Subtract 2 to both sides. So y is equal to 3x minus 5. So again, you'll notice the big comparison is that the slopes of these two equations are opposite and reciprocal, which is required. Notice I did not reuse the same y-intercept. I had to find this y-intercept given the new ordered pair 1, -2.
Excellent.